I'm Charles de Cagnadio. I'm researcher at the Bristol Composites Institute from the University of Bristol, and today I'm going to talk about work on a paper that we've published in Material Design called Design Space and Manufacturing of Programmable for the Printed Continuous Flax Fiber Polylactic Acid Composite Hygromorphs, and especially how it's used to design soft robots. And so the title of the presentation is Humidity Actuation, Material Selection and Design. I'd like to thank all my supervisor for all the help, and the STL, EPSRC, and ERC for the sponsor. So basically, soft robots are materials which are made out of compliant materials, so in which the stiffness is not as high as metal, for instance. If you look at Wikipedia, you usually see that the control for soft robots is usually electric field, thermal, with shape memory behavior, and pressure in case you have inflatable soft robots. And there's always one which is forgot, it's like the little brother, humidity. So humidity could also be used to control soft robots. And one of the soft robots that are available in nature is a pine cone. Basically, a pine cone open and closes um, depending on the humidity surrounding it. It's a natural selection process which has been optimized in order for the pine cone to reach seeds at the exact good time. And the way it happens is you have the pine cone scale which has a bilayer structures. So it is made, as those two layers are made of similar polymers, but inside those polymers are different holes. In one of the layers, there are circular, rough spring-like holes, and the other layer, it's smooth, square holes. And these different holes create different width of expansion when in contact with humidity. So one of the layer basically wants to expand, the one doesn't want to expand that much. And so you create stresses at the interface of the two layers when humidity changes, and therefore bending. And that's how the pine cone closes and opens. That's one of the soft robots available in nature. And if you think about it, this time that it needs to actuate could be considered as another dimension, as a dimension. And so if you 3D print similar structures, it would create a fourth dimension as time, and therefore that's why we create 4D printing. And that's mostly what we're going to talk about today, 4D printed humidity control structures. So we're going to talk about mostly structures. This presentation is going to be structured about a literature review that we've produced in advanced functional materials. And then the example are going to be from the paper we're discussing today. We discuss conditioning, mechanical properties, speed, repeatability, design model, printing path, and type of actuation, material selection as well. So if you see a teddy bear on the bottom left of your screen, it's basically because it's a soft and it's a robot teddy bear, so it's a soft robot. And the reason why it's made out of wood is because wood is a natural fiber that is hygrophilic. So basically it absorbs water. So where it absorbs water is via its hydroxide group. And you need this water absorption capability in order to be able to absorb humidity and then have an actuation out of it, create the motion that we require to have a soft robot. And so that kind of soft robot that we're going to talk about today. So there are two main shapes that are available with that kind of soft robots, bending and twisting. So bending, I've already explained, and twisting consists in curling the specimen on itself. In this presentation, we're mostly going to focus on bending though. So I want to highlight different parameters we could use in order to understand the deformation that is happening on the soft robot. Multiple parameters in which you have different trackers along the side, along the specimen, and these trackers you follow the displacement and the positions of the different trackers to understand the complex deformation of soft robot actuators. You can also do it with a single parameter, for instance, kappa, which is a curvature, eta, which is a deflection, and alpha, which is a bending angle. And this represents the overall deformation of the specimen. For this presentation, I just want to highlight that we're going to use a lot of kappa, and it represents the overall curvature of a specimen. So first, we're going to talk about the actuations of structures available to create a kind of soft robotic actuators. So three different structures are available. Continuous fiber composites, discontinuous fiber composites, and biomaterial structures. So for A and B, so continuous and discontinuous fiber composites, the principle is the same. Basically, you have orthotropic materials. These materials have different properties transverse to the fibers and in direction of the fiber. So if you print the different layers with different direction of fibers, then the different layers will have different will of expansion when conducted with humidity, and therefore you are back in the situation of the band cone. When one layer wants to expand, the other one doesn't want to expand that much. You get stresses at the interface, so bending basically happening. For the third proposition, B material structure, it's a bit different. It's not so much the orientation which is important, it's the distribution of material. So you have two different materials that behave differently with humidity. One wants to expand more than the other. So if you distribute this material differently between the different layers have different will of expansion again. And so you have different, and if you contact these two different layers, you have stresses at the interface and so bending and actuation once again. This last part, we're gonna not focus too much on it. So one of our co-authors for the literature review is Frédéric Demolly. He's one of the world experts in this field of the material structure, so you can have a look at his work. We are from the Bristol Composite Institute, so we're going to focus on the two first elements, continuous and discontinuous fiber composites. And an example of a continuous fiber is continuous flax fiber reinforced PLA, and discontinuous would be flax fiber reinforced alginate peroxide hydrogel. So both flax fiber composites, but with different type of structures. So in this literature review, we define two different types of actuators, fiber-dominated actuation and matrix-dominated actuation. This concept are different because in the fiber-dominated actuation, the humidity triggers the deformation first of the fiber, and then the fiber expand and contract, and then push and pull the matrix, and this creates the overall deformation of the layers, and therefore of the entire structures. For the matrix-dominated actuation, it's a bit different. There's a matrix that wants to expand and contract, and the fiber in the fiber direction does not want to move, and so it's going to prevent the deformation of the matrix in the direction of the fiber. And therefore, if you print with different angles, different layers, the fiber is going to constrain the matrix in different direction, and therefore you can get actuation of your structures. Then this lovely robot is chilling in a sauna. So basically, it's being conditioned basically in humidity. So we want to highlight very quickly how we can create conditioning of humidity for our soft robots. There are 5 different ways that we've highlighted to be used in the lab: air to water, oven, passive desiccator, and active desiccator. The two most common are air to water and water to air, because it's very straightforward and you get a large actuation, so you understand the capability of actuation of your material. But you only have one value of actuation available, and it's fairly difficult to repeat because you have a temperature, it's difficult to control, and the temperature is always related to the humidity. And so you need to control both if you want to have perfect control of your actuation. To get more different actuation, researchers use desiccator, especially passive desiccator. It's boxes with salt inside, and this salt controls the humidity inside the box. And therefore, you are able to have different humidity for your specimen to control actuation at different level of humidity. If you want more control with the humidity and temperature, then researchers use active desiccator, which are desiccator in which you don't need to open the box to change the humidity. You can just control it from the outside. Therefore, you have very good control of the actuation. Another aspect that is interesting for us is the mechanical properties, because the mechanical properties influence the actuation, and also because the actuators are usually multifunctional structures. So they need to actuate, but they also need to interact with the environment. And so you need to know if they're going to be able to interact with the environment with the stiffness that they had. They're not going to be broken by the environment, basically. So what we did is like we tested different types of material for our 4D printed endeavor. Alginate-based hydrogel, short fiber 3D printed and long fiber 3D printed. And we're able to see that depending on what you want, you have different type of mechanical properties available. So the red arrows present material that we have tested for 4D printed application. So, and we've created databases for all the material that we could, similar material that we could find in literature. And so we encourage you to have a look at these databases if you're looking for a material. So you can see that for the first red arrow on the left, the alginate-based hydrogel has a stiffness approximately 0.1 gigapascal. The short fiber 3D printed has about 1 gigapascal in stiffness, and the long fiber 3D printing has about 10 gigapascal in stiffness. And so basically, all this material could be used for 4D printing. You can just choose the stiffness that you want, depending on the function that your actuators will have. Another aspect that I'm not going to go into much details, but when we started working on natural fiber, there were not clear guidelines on how to measure the porosity of natural fiber composites. However, porosity has an impact on actuation and on mechanical properties, because there's an impact on water absorption as well. And so we created sort of a comparison between different techniques for measuring porosity: gravimetric measurement in water and ethanol, CT scanner, optical measurement, SEM, and tensile test. And we provide some guidelines in order to assess the amount of porosity in natural fiber composites, which is a good way of understanding how the porosity is going to be influencing the actuation later on. So we published a paper specifically on this one if you're interested about the type of property. Now let's go back to actuation, and especially speed. So how does our actuator actuate, and how fast it is? So there are two aspects to speed. There is the reactivity and the time of convergence. So basically, if you have a sequence of actuators working with each other, you want to know when they're going to reach their final point, so that you can make sure one reach before another one and before another one. However, you also might want to have actuators that are fast in actuation, that are very reactive, to be able to change something quickly. And that's what we call reactivity. And so these include two different parameters. These two parameters are presented here. So alpha is a reactivity. Basically, it's a derivative of the function of the curvature against time. And we presented initially at 0, but you can make it at any time. And the tau represents the time of convergence, is the time at which the actuator reach a position, a certain percentage from its final deformation shape. So I'm going to give you an example about a kind of test. So here you have a square specimen on the left in a box. So this petri dish means that there is some salt inside and water, which makes the box at 98% humidity. So the material is going to actuate basically. You can see you have two cameras on one of each side, and on the image you can see little trackers, basically 6 different little trackers. These trackers will be used in order to position the deformation of the material in space. Then you obtain 6 points that you correlate with a circle, basically, and you measure the curvature from this circle. Then you plot the curvature against time, and you are able to measure the time of convergence and the reactivity, so alpha, from this curve. So this specimen are a bit specific because they have 3 different layers. So one layer is transverse, and the two other have an angle alpha and minus alpha. And then you can vary the angle alpha to see the impact of the angle alpha on the speed of the actuation. So these are the curve that we've obtained, so the time against the curvature against the time. And we were able to see that the fastest in terms of reactivity are the specimen 40 degrees, 45 degrees, and 50 degrees. However, they were also the slowest to reach their convergence time. So basically, you can modify the value of alpha in order to obtain a fast or a reactive material, depending on what you want. So that's a way of designing an actuators in terms of speed. So that lovely soft robot want to do reps at the gym, and so he wants to know how much he can do so that you obtain the same motion for the same solicitation, for the same humidity, basically. And so in order to do this, you need to test the reversibility of the material. So we define in our literature review the reversibility as a 3-step process in which you have the reference actuation. So you condition your actuators in a specific humidity, let's say alpha %. You measure its actuation, so let's say kappa I, which is the initial curvature, and you give it an actuation history, which is conditioning your specimen for N1 relative humidity, or N2 repeat during N3 days, weeks, hours, whatever you want. Then you condition it back to the initial relative humidity, alpha %. You measure its deformation again, and you compare kappa F to kappa I in order to know if your material is reversible or not. So we are testing currently the reversibility for our material, and we provide the database because it's a very complex test to conduct. You have an infinite number of actuation history possible for your material. And so providing a database is very essential in here to understand what has been done and what could be the interesting actuation history to give to your material in order to understand the repeatability or not of the actuation that you create. Another aspect that is interesting for us is modeling. How do you model that kind of actuator? So this man is creating a soft robot, designing it. What kind of model could you use to do this? So we define 5 different types: Timoshenko, classical laminate theory, voxel, non-voxel FEA, finite element modeling, elastic energy, and voxel-based technique. So Timoshenko equation is a bilayer beam analytical equations that is related to the um, properties of the different layers of your actuators. If you have the stiffness and the thickness, basically you can estimate generally the shape of your actuation. You can also complexify this model, so that's what we did, in which we created sort of a finite element Timoshenko, in which we put Timoshenko beams next to each other, and we were able to assess the the deformation of a material in which the properties of the beam change along the length of the actuator, basically. So this model, which complexifies Timoshenko, is available in the paper we published in additive manufacturing, you can see at the bottom of the screen. Then for straight fiber and composite material, classical laminate theory is also analytical set of equations that can give you the deformation, but it's limited to certain materials and certain printing path. For bilayer structures, but also for more complex printing pattern, you can use FEA models. It's very efficient for bimaterial structures because you can distribute your two materials that have different expansion capability as you wish. So very straightforward. Then if you want to refine even more and have more local understanding of the behavior of your material, elastic energy and voxel-based modeling are interested because you can define properties of your material very locally. For instance, you can CT scan your material, assign properties of your to every single voxel that you obtain, mechanical properties, and build an actuators from this technique. We also wanted to create our own model, and so we were inspired by a walk in the park in which we saw leaves curl on the ground. So when they fall from the trees, leaf dries and then tends to curl. So we wanted to see if we can reproduce an actuator that is able to curl same as a dry leaf. So what we did is like we look at the back of the leaf, look at the vein pattern on the back of the leaf, create a layer which has a similar pattern basically, and then the second layer in D shows the second layer which is transverse to the initial vein pattern layer. So that's our actuator. Then we consider these images of a printing path, and we turn them into images. From these images, we're able to obtain the local fiber orientation and amount of material. And so we could assign to a finite element model the local mechanical properties, actuation properties, and orientation of the fiber to every single finite element in the model. And therefore, we could understand local printing pattern for our model. We run this model. We also printed the specimen. You can see at the bottom, we condition it between 11% relative humidity to 98% relative humidity. Compare the model to the test. We're able to see that there is a bit of difference between the two, and we explain in the paper why we see this difference. But this model is interesting because we parameterize, if you parameterize your printing pattern, so your printing path, you can link your printing path to the actuation you get at the end. And so you can say, I want this actuation. With an optimizer, you can go back to you can optimize the printing pattern that you need to get this actuation and optimize your design, basically. So that's one of the benefits of this technique. The other benefit is that it enables you to understand the local actuation of your material. So this is a specimen that I've already talked about in the past. One for 45 degrees on the top and 85 degrees at the bottom. And this is the model that we've created applied to this type of actuators. So this is FEA model, so the yellowish, reddish colors represent high stresses, while the blue represent low stresses. And with this model, you are able to understand exactly the spot where your actuation comes from. And so you understand what is the link between your geometry, your pointing path, and the actuation you obtain at the end. For the 45-degree specimen, for instance, you see that the actuation comes from a bit everywhere in the specimen, whereas for the 85, it's much more distributed on the edges, the high pressure that creates, the high stresses that create the actuation. And so that's also one of the benefits of this model. So our work in the park with our soft robot. Our soft robot wanted to also become a flower, and this is a calla flower, which is a common flower used as an inspiration for soft robots because of this curl shape, basically. So we want to obtain this curl shape from a plain printing structures. That's what we did. So this is a printing path on the top left of the screen with the two layers. We 3D printed this, then conditioned it 11 to 98% relative humidity, obtain this actuation, which is very different from the one of the flower that we've seen before. Basically, we didn't have enough double curvature and we didn't have enough actuation overall. So what we did is we wanted to try implement a technique to improve these two aspects of increasing the actuation amplitude. So this was the role of this specimen that we've shown already several times during this presentation, in which you have different angles for the different layers. And we wanted to see if the angle alpha can modify the amount of actuation that you get outside in the specimen. So we varied the angle alpha and tested it for different values, and we're able to see that at 40, 45, and 50 degrees, you obtain much more actuation that you obtain at any other orientation. Usually for actuators, most people use a 0.90 stacking sequence. So if it's a value of alpha was 90 basically, and we prove that we are able to increase the amount of actuation by changing this angle of alpha. So another aspect that we wanted to look at is curving the printing path. So instead of having straight fibers, we wanted one of the layers to have curved fibers basically, and see how this curved fiber would impact the formation of the specimen. So we've reprinted the printing path on the left, conditioning between 11 and 98% as usual, and then obtain its 3D shape with a DIC as the previous specimen we did. Then we define, it's a circular specimen, so we define what we call angle of measurements, which are different angles in the radii of the specimen, in which we were obtaining different points and then obtaining the circle that we used to obtain the curvature for these different angles, basically. And so we could measure the curvature against the different angles and against the time, as you can see at the bottom center of your screen. So we obtain this normalized curvature for different time and angle of measurements. And this curvature is plotted against the angle of measurement, so the different angles in the radii of the specimen. And this graph shows that basically the more straight the fiber are, the more actuation you get. And so we were not able to improve the amount of actuation we could get by bending the curved fibers, but we were able to control the actuation by bending the curve, by curving the printing path. And so that's another way of controlling the actuation, basically controlling the printing path of your soft robots. So we've shown different ways of controlling the printing path, but as you can see on this specimen, in the example of the specimen, so 30, by the way, means a radius of curvature for the curved fibers. So the fibers are curved, but they're also very compacted onto each other. So we were wondering, can we dispatch the fibers so that there is only contact point between the first layer and the second layer, and maybe we can control actuation by doing this. So we took our soft robots to a trip in Paris, and in Notre Dame, as you can see in the middle, there's sort of a circular shape, basically. And we thought about this shape and tried to create something that represents that kind of circular flower shape. That's what we did. So I agree, it doesn't look a lot like Notre Dame, but still the inspiration is there. And the first layer are concentric circles, basically. Second layer is more of a flower shape, and every single actuator is a contact point between the first and the second layer. And so the actuation of the entire structures is controlled by the position of the contact points, the number of contact points, and the angle between the first and the second layer for each contact point. And so we can create complex actuation out of it. So this was made with much softer material, much easier to print, and it's flax fiber reinforced alginate hydrogel, and you can create that sort of complex actuation. And the type of materials has specific purpose for biomedical application, for instance, to deliver drugs or to replace soft tissues. I would like to thank you for your attention, and I'd like to thank all my supervisors, Antoine, Adam, James, Fabrizio, and David. Thanks all of our sponsors and Ecotechnia who help us with the fiber. And if you want to have a bit more idea about 4D printing, please have a look to my YouTube channel where I publish presentation for the papers that we publish.